The world is full of people telling you who to believe they are. Well, we thought we'd tell you who we're not. Let's start here. We're not in shipping. We don't make lifts. Seriously, no lifts. We do this. We're good at this. And we make all of these. And even though you'll find us here and here, we don't make energy. We make you save it. And you'll be saving the environment too. Are we an internet company? Well, we connect and power just about everything around you, helping machines talk to each other and to you, making your world more personal. We're seeking out the big questions and answering them honestly. Like, how can we make the most of our energy and resources? Or can we make access to energy and digital basic human rights? We're real people, employees, developers, partners, investors, and inventors, all passionate about doing what's right. We're open. Humans of all sorts from all over, learning from each other and about each other. We're not here to save the world. It'll go on with or without us. We're here to help power and connect what you do every day, to ensure life is on everywhere, for everyone, at every moment.
Buenos días.
Okay, Jorge, want to take it away?
Buenos días. Bienvenidos a nuestro webinar Soluciones de energía de Misión Crítica, enfocado en los tableros de transferencia serie 7000 de ASCO Power Technologies. Mi nombre es Jorge Parapar, soy el Business Development Manager para ASCO Power en Latinoamérica y seré su moderador para este evento. Hoy vamos a tener la oportunidad de contar con la presencia como speaker de Víctor Bonachía, nuestro Product Strategy Director. Antes de comenzar, me gustaría mencionar que disponemos una ventana de chat para que puedan realizar preguntas durante el evento. Tenemos también algunas preguntas muy comunes que nos han hecho nuestros clientes durante sesiones y eventos anteriores. Estaremos llevando un registro de las preguntas y trataremos de responder la mayor cantidad posible a través del chat y durante los minutos finales del webinar. En caso de no poder hacerlo en todos los casos durante el evento, buscaremos responderlas posteriormente. El webinar será impartido en idioma inglés, pero las preguntas en el chat pueden hacerlas en español. Igualmente, las respuestas en el chat serán en español. El webinar quedará grabado y le agregaremos subtítulos en español para que puedan consultar el video nuevamente si lo desean. Sin más, le doy la palabra a Víctor Bonachiva para que pueda presentarse con ustedes.
Gracias, Jorge. Yo hablo un poco de español, pero mi inglés es mucho mejor. Entonces, como dijiste, voy a hacer la presentación hoy en inglés, pero cualquier pregunta, mete en el chat y Jorge puede responder en español. Gracias. So switching to English now, a little bit background and introduction to myself. My name is Victor Bonachia. I am the Product Strategy Director and Expert Product Owner involved with R&D and development of new products at ASCO Power. I've been in the industry for 12 years with a background in electrical engineering. That's my bachelor's with power and controls as a specialty and a master's in engineering management. I have several patents around the space of transfer switching and controls. And I'm also heavily involved with codes and standards committees through IEEE, as well as NFPA, developing codes and standards around the space of transfer switching, standby power, and backup power applications. Today, we're going to cover several topics. We're going to do an introduction to ASCO at a very high level. What is ASCO? What is our full scope of supply, and what do we bring to the market? We're going to talk about the basics of transfer switches. We're going to start very basic and then move our way up and quickly get to more complex topics around switches. Talk a little bit around the codes and standards involved with them, some of the contactor design concepts, as well as a little bit more information around the controls and different types of transitions that can be done with transfer switches and the benefits of certain transition modes in certain applications. During the webinar, we will also have 2 videos demonstrating actual product, live product The videos are pre-recorded, but filmed right here in Florham Park, New Jersey, which is where the ASCO headquarters is located in the United States. So who is ASCO? We are a global manufacturer of electrical equipment. We really specialize in switching and control products. We have several key product lines that belong to our portfolio, including transfer switches, power control systems, sometimes also known as paralleling control systems, and power control and monitoring software and devices such as meters, electrical monitoring software, and network equipment to support that infrastructure. We've been in this space for over 125 years, producing various products, all stemming from our core development of the solenoid operator, which I'll talk about more. And we are industry leaders in source management, controlling multiple power sources to feed individual loads. We've pioneered technologies that have been globally adopted by other manufacturers in the transfer switch market, and that further reinforces our leadership in the market with technologies such as overlapping neutral designs, in-phase transfer, and blow-on contact technology. And together with Schneider Electric, which acquired ASCO in 2017, we can provide a full scope of supply from every component in your power chain, from your source all the way down to your load. So every level of distribution, control, and protection that's required between ASCO and Schneider together, we can provide that, building up the entire electrical system in a facility. We serve all sorts of markets around the world. So we are not just in the US, we have a global presence serving education, government, water treatment, and many, many more types of locations and applications and segments, stemming from very simple applications such as residential and commercial retail transfer switching, all the way up to the most complex data center, water treatment, and healthcare applications that are extremely critical for life safety. So we have a huge level of experience with all sorts of applications out there and are able to scale our solutions for those markets as needed. At the end of the day, our job is to be here to provide equipment to keep your critical power on. The number one goal of the ASCO division of Schneider is to provide solutions, equipment, and products that will ensure that when your utility power fails, we are there to back it up and provide all the controls and equipment needed to get your critical loads onto an emergency power source. Now, our core product, our most well-known product is our transfer switch products, and that's going to be our major focus today, focusing on transfer switches and specifically our 7000 series transfer switch product. So let me start at the very basic level of what is a transfer switch, what are the jobs and major functions of a transfer switch, for those who may not be familiar with it. So a transfer switch is, in most cases, continuously carrying current while connected to the utility load as a passive device. So 99% of the time, not much is happening on the system. Power is flowing from your utility source down to your transfer switch while the source is good. However, if power were to fail, the transfer switch's job is to detect that power failure, send a control signal to an alternate source of power initiating it, usually a generator type source, that will start the generator to be able to provide emergency power and safely transfer the load to that emergency power source, reestablishing a continuous power supply to that load. It will operate in this mode until it senses the restoration of normal power in the utility power source. And when it senses that, it will then determine it is safe to retransfer back to the source, and shut down the generator safely and effectively. It does all that, but at the same time, it needs to also survive any potential faults in the system with withstand and close on currents. I'll talk about this further in the presentation, but unlike a circuit breaker, the job of a transfer switch is to survive faults in the system and continue to provide power to its load. So it must be able to perform its sequence of operations, which we just reviewed, while also being able to withstand and survive any potential faults in the system while it gets cleared by other pieces of equipment. There's a couple different types of transfer switches. We have automatic transfer switches, which are the most common and most popular that you'll hear us talk about. These are transfer switches that are automatically initiated by controls and a controller inside the equipment. It will detect the power failure and initiate the emergency source and transfer to it completely automatically. Does not require a user. And the transfer is electrically operated, meaning the switch contactor electrically will operate the solar mechanism, switching the contactor from being connected to one source to the other. Alternatively, there's also non-automatic transfer switches, which still have a controller, but require a user to initiate the transfer. These units are still electrically operated, meaning the contactor does not have to be manually driven, but a user must initiate the control. And this is important for applications where a high degree of human supervision and control is required before the system automatically takes any actions. And lastly is a manually operated switch. A manually operated switch has no controls or supervision to the controls, and the contactor is physically operated by the user by turning a handle. So again, the main difference is an automatic switch has a controller that will function automatically. A non-automatic still has a controller, but a user has to press a button or send a signal to the switch to initiate the transfer. But a manual switch has a physical handle that somebody must physically turn on it to transfer to emergency power. ASCO has several types of transfer switch platforms, ranging from our Series 185 platform, which is our simplest and least configurable product, really meant for residential and small scale applications. In the middle range, we have our Series 300, meant for more commercial applications that offer some more degrees of configuration within the controller, with time delays and pickup and dropout settings for voltage trip levels, and has some options. But today's presentation will mostly be focused on the 7000 series transfer switch, which is really geared towards critical applications such as hospitals and data centers. And these solutions are built to customer specification, are highly customizable with an extensive list of accessories and options that can be added for every need a customer may have, and highly configurable with its settings and sequence of operations options that can be implemented in it to meet, the needs of your facility. So we're going to focus today mostly on talking about capabilities and features within the 7000 series family of products. A very important topic around any transfer switch product or any critical power equipment is the codes and standards that apply to it. I'm going to focus a little bit more on the standards today, but just to make sure we all understand, the difference between a code and a standard is that a standard applies to the performance and manufacturing of a piece of equipment or a product itself usually, while a code has to do more with the application of that equipment in different types of facilities and environments. Today, I'm going to mention two standards that are critical to understand in this space, which are the UL 1008 standard, which is the NEMA and primarily North American standard used for denoting the performance requirements and manufacturing requirements for a transfer switch. As well as IEC 60947-6-1, which is it's very similar to UL 1008 in the sense that it is the product performance and manufacturing standard for what started in the European market and has then expanded to other regions globally as the standard. So which standard you adopt many times has to do based on your geography, as well as user preference in some cases, whether you are looking for a product as UL 1008 or IEC 60947. Luckily, ASCO products are qualified to both standards and can be applied, and the correct standard can be applied based on what your needs are for your specific order. As you can see at the bottom here, one of the most important things the standard controls, besides guaranteeing that the product is manufactured to a certain level of quality and performance, is around the short circuit ratings and WCR ratings, which we'll talk about in more detail later, which are different between the two standards. And that is due to the fact that the standards have different testing requirements, which could result in different levels of rating for the same product across both standards. On the left, you can see the ratings table for our equipment with UL 1008 testing applied. And on the right-hand side is a similar table for the IEC ratings of that same equipment. Of course, I don't intend you to actually read it on the screen, but it's just a reference, and you can, of course, always access the full ratings documents on our website. But one thing to consider when looking at the difference between the standards is that they are not necessarily apples to apples. They are not necessarily equivalent. It really depends on your needs, as I mentioned. And the UL standard is generally considered a more robust standard, while the IEC standard around transfer switches is sometimes not as robust because it allows to various levels of performance, which could become difficult to coordinate and confusing. For example, the IEC standard allows for different category levels or utilization categories, such as AC 33A, 33B, 32A, of which you can qualify to any of those that you select. However, the level of performance between these standards and the testing required to qualify is significantly different between each of those. As you can see in this example, a difference of an IEC qualification to the 33A utilization category requires 50 cycles of overload testing for most ampacities, while one step below that, the AC33B, only requires 5 cycles of overload testing. So the performance and testing required to gain the qualification is significantly different, and you have to pay very close attention to product qualifications, which category and utilization level you are specifying the product for. UL 1008 only really has two rating levels, but primarily everyone in the market only qualifies to the more advanced rating level for emergency standby systems, which is outlined here, and is in line with the more strenuous level of testing that you see for AC33A here. So overall, the UL standard is more closely aligned with the most stringent level of the IEC certification, leading to that conclusion. I briefly touched on the concept earlier of ratings and what we call WCR ratings. This is more of a UL 1008 terminology, but a very similar concept exists in IEC ratings as well. So I'll just use the UL terminology for the sake of this conversation. Circuit breakers, which many people are familiar with, have a KAIC rating. An ampere interrupting rating is really what that represents. And what that means is, what is the short circuit fault capacity that the breaker is able to safely open under without sustaining extensive damage? So how big is the fault that that breaker is rated to interrupt? And by interrupt, that means opening the breaker to end the fault condition. Its number one job being protection. A transfer switch is different. A transfer switch is not meant to provide protection against fault. It's meant to provide power resiliency to transfer and manage power to your sources. Its real intention when it comes to fault scenarios is to withstand and survive the fault. And that's where WCR comes from, and that stands for withstand and closing rating. So that really means that if there is a fault on your electrical system, the transfer switch must be able to endure the fault for the duration of time that it takes the circuit breaker to clear the fault and still be able to operate effectively and safely afterwards. Additionally, it must also be rated to close onto a fault scenario. So again, the ATS is going to survive it and withstand it. The circuit breaker is going to interrupt it. So the requirements in the design of these products is very different, because one has to survive it for an extended period of time, while the other one has to interrupt it, and it has different characteristics that go into the design consideration between those two things. So do not confuse the KAIC rating of a breaker with the WCR rating of a transfer switch. That's the main message there. To further illustrate that example and why WCR ratings are important, I'll use this graphic here. So on the left-hand side, I am showing the example of a non-selectively coordinated facility. ATS is positioned at several layers in the system, but let's pretend there is a fault at the lowest layer and the circuit breakers are not selectively coordinated. If the circuit breakers are not selectively coordinated, that means that their tripping times are not necessarily in line with each other. And even though you have a fault down low in the system, a circuit breaker much further upstream may be the one to trip, the one with the X over here, because they are all non-coordinated. They all trip in about the same amount of time. And that takes loads offline out of service unnecessarily. There is no reason, if there was a fault on this branch down here, for it to also take down this branch up here, for example. When you selectively coordinate your circuit breakers and your transfer switches, what happens is that the breakers closest to your loads must trip much faster than the breakers that are further up in your system. What that means, if there is a fault lower in the system, that breaker will trip before any breaker above it, minimizing the unnecessary power outage to other branches in the system. The transfer switch's WCR rating is then important because the WCR rating is composed of two numbers. It's composed of a duration of time as well as a level of fault current. So for example, on this table, we can see that this J-frame ATS, or better said, this H-frame ATS down here at 480 volts can withstand 36 kA of current, 36 kiloamps, for a duration of 0.3 seconds. So that means that ATS can be applied in applications further and further up the chain, where your fault current may be higher the closer you are to the source, and where your withstand duration, because the circuit breakers are coordinated to trip slower the further up you go, the ATS is coordinated to go with that breaker. So down here, this ATS only has to withstand, this ATS only has to withstand a fault for 0.1 seconds, while one up here must withstand a fault of 0.15 seconds, and so on and so forth. So you need to make sure you selectively coordinate, and that has many advantages. If you do not selectively coordinate, you can over-engineer a project, get a transfer switch with an extremely high rating for an extremely long duration, but that will be a very large piece of equipment and very costly piece of equipment. Selective coordination not only minimizes the loads you take offline in a fault, but also allows you to use properly rated equipment for your application, allowing you to use more cost-effective and smaller footprint equipment, because you're not over-engineering for the largest and worst case possible scenario. So that's a very important topic to keep in mind. So at this point, we're going to switch from talking about code and standards to talking about actual product. And I'd like to kick that off by showing a video of one of our 7000 series transfer switches and a walkthrough of that product before we talk about some of the design characteristics of it. Hi, my name is Victor Bonachia. I'm the Director of Product Strategy at ASCO Power Technologies. I'm here today to talk to you a little bit about our 7000 series power transfer switches. Transfer switches are used to connect two sources of power to one load. And what they really do is connect to a utility source majority of the time, but when power fails on the utility source, it detects that, starts a generator, and transfers to generator power, keeping your loads online. When utility power returns, it detects that, reconnects to utility power, and then shuts off your generators, making sure that those loads have transferred back and forth safely and effectively. This is an example of our 7000 series transfer switch. We also make 7000 series bypass transfer switches that we'll talk about soon in another video. The transfer switch really has a couple of key parts. In most applications, the equipment is sold in an enclosure, and that enclosure contains a controller with some interface buttons and status lights, as well as the transfer switch itself, which is the device that carries the heavy-duty current and power from your multiple sources down to your common load. In this example of a transfer switch, let me walk you through some of the important areas of the equipment. Now, this equipment is de-energized, so I can easily access it and show you parts of the equipment. The first area I'd like to focus on is on the left-hand side over here. This is known as the operator mechanism, or the solenoid operator. This is the device that provides the mechanical motion that drives the shafts, opening and closing the contacts on the two power sources. In this example, it is a single solenoid operator, which is used in our open transition switches. The single solenoid operator provides a very fast transfer, simultaneously disconnecting from the connected source and reconnecting on the other source. Alternatively, you can also have a dual coil transfer switch or dual solenoid, which would provide a second coil down here. This provides you with the ability to control the normal power shaft and the emergency power shaft independently and control those contacts independently, meaning you can disconnect from power and wait a period of time before reconnecting to another power source, allowing your loads to fully de-energize before connecting to that other source. Alternatively, it can be used to connect to the second source before disconnecting to the primary from the first source, giving you a closed transition operation, meaning a blinkless, outage-less transfer between power sources that is transparent in most applications, meaning no facility downtime during that transfer between sources. As I mentioned, the solenoid operator provides the mechanical motion driving the shafts which the contacts are connected to. This allows the contacts to close and open on different sources of power to feed the load. Those contacts and pole assemblies are located below these plastic pole covers. Here you go. Thank you, Prasanna. There's a lot going on under these pole covers, and this is really the heart of the transfer switch. Looking from the top and the bottom, the first thing you see are the lug assemblies. The lugs are where you are connecting your power sources and your loads to the system using cabling. From there, it goes to some busing and the main contact and shaft and contact assembly. In this area, you have a couple sets of contacts and different connectors. You see two sets of contacts, one for each power source. But the contacts are actually two types of contacts for each source. Below, you can see the main contacts, which are long, flat, piano key looking pieces, which carry the current during the normal operation of the transfer switch. Up top, you have the much smaller arcing contact. The purpose of the arcing contact is to divert the arc to the arcing contact during an opening operation. This protects the main contacts from being exposed to that arc and minimizing damage and corrosion to those contacts during the operation of the equipment, extending the life of the total transfer switch. The arcing contacts are designed to be easily replaceable and inspectable. Additionally, the arcing chute, which is composed of these metal blade pieces, is used to magnetically pull the arc away from the arcing contact as it transfers, extinguishing the arc as quickly and safely as possible. A major focus of our transfer switches is the ability to inspect them, maintain them, and service them. All of our transfer switches include a maintenance service handle on the inside. This service handle can be easily detached and put into the service handle connection to transfer the switch back and forth during a maintenance operation, so you can inspect the motion, the mechanics, and state of all the contacts. This is meant to be done only as a maintenance operation and not while the equipment is energized or under load. A simple but often underappreciated part of the transfer switch is the customer terminal block. In the installation of a transfer switch, many times there are signals from basic signals such as an engine start signal to a generator, or other control signals from external systems that have to be connected. In ASCO transfer switches, those signals have been centralized to the top right corner of our enclosures, providing one place for the customer, contractor, and installer to land all their connections. The exact functions of each terminal are spelled out in the wiring diagrams that ship out with every single transfer switch, and can also be accessed using the QR code on the front of the transfer switch, which provides you the drawings and outline diagrams for each serial number unit. If the main switch is the brawn of the equipment, the brain is the controller. The transfer switch controller has a couple important job functions. It is monitoring the status of both sources of power, anywhere between 120 to 600 volts, depending on your configuration. Determines based on the power characteristics whether that source is considered acceptable and healthy, or whether it is unacceptable, and therefore the generator must be started and the equipment must be transferred. The transfer switch includes the main control assembly in the back, with an exposed HMI in the front, where a user can access all their configurations, time delays, settings, voltage configurations, and pickups and dropouts, which can all be customized to the site's specific requirements. Additionally, large LED status indicator lights provide the status of the equipment, letting even any contractor or end user from a distance quickly and easily identify what the status of his power sources are, what source the equipment is connected to, and even initiate a transfer. So let me demonstrate now to you a couple of the most basic sequence of operations for a transfer switch. Again, this is an open transition switch in a controlled environment right now. And we're going to start off by doing a transfer test the way someone would do if they were testing the equipment. As we can see here, the utility source is accepted and the transfer switch is connected to the utility source. If I go ahead and I hit the transfer test button, it will send an engine start signal, wait for the generator to come online, and then the equipment will transfer to the generator source, proving that the equipment and your entire system is functional. Once the transfer signal is received, the equipment will go ahead, count down, retransfer to the utility source, and momentarily shut down the generator after a cool down period. Our transfer switches come in a wide variety of configurations. For NEMA applications, they are qualified to the UL 1008 standard. And for IEC applications, they are qualified to IEC 60947-6-1. They also come in many types of enclosure configurations, from open style switches to be integrated into other equipment, to type 1 indoor enclosures, type 3R outdoor enclosures, stainless steel enclosures, and many other options depending on your environmental requirements. We also have many accessories that are optional to add. While the controller is standard on every unit, the controller is responsible for voltage and frequency monitoring. However, many common accessories include communication outputs such as Ethernet and Modbus, metering that gives you power, energy, harmonic information, and more, as well as many other accessories for all your I/O and control needs. Please ask your local salesperson for guidance if you need help identifying any specific accessories. Beyond that, we are also rated from 30 to 4,000 amps and can have the option for a service entrance rating, which bonds your neutral conductor to your ground when this is being used as a service entrance device. It was very informative by seeing the actual product in a real world model, not just pictures on a slide. But let's talk a little bit now about the concepts that I introduced in the video. So a transfer switch really is made up of three key areas. The one area is the controls, which are the brain of the equipment and govern the sensing, the sequence of operation, when should it transfer, the time delays, all that. Another part is the transfer switch itself, transfer panel, contactor. You may hear all those different terms. It is the same thing. It is the device that is actually carrying the current from the sources to the loads, and that's doing the physical switching of the equipment. And in many cases, also the enclosure in which these two pieces of equipment are mounted in. The controller and the switch are mounted inside an enclosure in many applications, indoor enclosures, outdoor enclosures, or in some cases, no enclosure is provided so that the switch and the controller can be mounted into other pieces of equipment or switch gear, integrate a solution. Let's talk a little bit about the switch itself. So the ASCO platform has many different switch frames based on the ampacity of the equipment, really, ranging from the D frame, which goes from 30 to 230 amps, several ranges in between, all the way up to our largest, which is our 4,000 amp frame. All the frames are rated up to 600 volt applications, and the WCR ratings, the withstand ratings that we discussed earlier, vary based on the configuration and the breakers that are used. So please refer back to the rating tables on the website for those exact ratings. The switches really are composed of two key areas, like I mentioned in the video. There is the operator, and then there's the pole assembly, which is where the switching between the sources actually happens to feed the load. Let's take a closer look at one of those pole assemblies and switches. Again, so you see the operator on the left-hand side here, followed by several pole assemblies based on the pole configuration of the switch. You can have a single phase piece of equipment with only 2 poles, or you could have 3 poles or 4 poles, depending if it's a 3-phase system. And if you are switching the neutral or require a solid neutral, all those things would contribute based on your needs for the application. We talked a little bit in the video about the contacts and the contact technology used in majority of our frames, how it's composed of really 2 independent contacts. A main primary contact, which is carrying current majority of the time when it's feeding the load, as well as a arcing contact, which is meant to take the arc of the equipment and not expose the main contact to that arc during an opening operation primarily. What does that look like? How does that happen? Well, below here, you can actually see a very broken down sequence of what it looks like as the contacts are opening in the switch. So below, you can see that normally when that contact is closed and you're connected to that source, both the main contact and the arcing contacts are in a closed position. Current is flowing through both sets of contacts. However, due to electrical laws, the majority of the current is, of course, flowing through the main contact at that point in time. And it will stay in this state for an indefinite period of time until it requires to open that contact, say during a transfer to the other source. When you're opening the contact, the main contact will disconnect first. And for a very brief period of time, all the electrical flow will be flowing through the arcing contact because it will still be in a closed position. The main contact opens first, then the arcing contact. As the arcing contact then begins to open, it will draw the arc upon it, but that is the entire point of the arcing contact. It is protecting the main contact, which is usually the piece that's conducting most of the current, is drawing the arc towards it and then flowing through the arc chute, which I will show in more detail on the next slide, until the arc is extinguished. And like I mentioned, the arcing contacts are designed to be easily inspectable and replaceable if necessary, although they usually do last the life of the equipment, and even when they're doing their job of protecting the main contacts. The arcing chute that I mentioned is this metal blade sheet looking component here. It's difficult to describe, but you can see how the arcing contact opens and closes by swinging through the grooves cut into the and channels cut into these metal sheets. The conductive nature and electromagnetic nature of these sheets pulls the arc away from the arcing contact, expanding it over a greater distance and area and cooling it down, which leads to the arc collapsing and ending the arcing condition and event more quickly. So the main point of the arcing contact is, again, to help very quickly extinguish that arc, because the arc is one of the areas, whenever you're doing any kind of switching, that leads to most of the wear and tear on contacts and equipment. So it really helps reduce the duration and intensity of that arc overall. Now, how exactly does all this motion happen? How does all this mechanical motion happen within the switch to open and close these contacts? Well, the transfer switch relies on the solenoid operator. There may be one, there may be two in the equipment, but the concept is the same. If you imagine the contacts mounted to a shaft, that shaft is represented by the red dot in this solenoid operator example. That shaft is mounted to essentially a wheel that is connected by a shaft to a pin that is inside an electrical coil. So this gray box is really an electrical coil, and this squiggly line here represents a spring inside the coil. When the transfer switch decides to transfer, what happens is that this electrical coil, the gray box, is energized, and that pulls in through a magnetic effect the shaft that is connected to the wheel, causing a rotating motion in that wheel, which in turn, if the contacts are connected to the shaft coming off of it, starts to rotate the contacts themselves. When that spring is fully compressed, the energy to the coil is shut off, and the momentum of rotation of the wheel carries the full rotation forward over this center position and completing a full rotation of the shaft that the contacts are connected to. So you can see here how it pulls up. So it pulls this up, rotating the wheel halfway, compresses the spring across these two steps. Then when we shut off current, that spring pushes the rod back out, completing the rotation of the contacts of the equipment. That's the basic concept of a solenoid operator. It's really just a spring, a coil, and a shaft that actuates linearly, but then is converted to rotational motion with this assembly down here. And that's the heart of the operator in our transfer switches. And that's very important because it's actually a very simple design. And a lot of times people look at very complex designs and call that elegant, but elegance is really in simplicity. And simplicity leads to reliability, because the more complex something is, the more points of failures there are, the more tolerant stack-ups there are. So you want to keep the design and the operation as simple as possible. And throughout ASCO's many, many years of design, including the transfer switch frames that are currently in production, we've continuously been improving on the performance of our product by learning from the industry, learning from new materials available to us, new manufacturing processes, etc., to the point that we do not look to just meet the bare minimum operation cycles that the requirements such as UL 1008 require, but we are continuously striving to improve the number of operations and the reliability of our equipment. In this chart here, we can show how over the design life of certain frames in our portfolio, we have continuously been improving them, going from meeting the standards requirements to significantly exceeding the standards requirements in many test cases. So it just goes to show how over time, continuous improvement is a critical concept to be applied in an area that deals with critical power applications and reliability of product. That's further reinforced by various studies that we have done on our very large install base that we have gathered over decades of experience. So we actually worked with a third-party organization as well as IEEE to do a reliability analysis and MTBF analysis of the amount of products that we have shipped to the field, and the operational time that those have had functioning in customer applications, as well as what have been the number of reported failures due to that equipment. And based on that data and some math that I cannot explain, I need quality to get involved to explain that, we've been able to do a MTBF analysis and availability analysis to show that the product has an MTBF of almost 1.5 million, but well over a million operational cycles. And the availability of that, when you look at it from a uptime point of view, is over 5 nines of reliability. So again, if you look over here, it's 1.4 million hours of operation, meaning that the expected failure rate is 0.06 failure per year if you look at the total install base relative to the number of failures reported. And then that results in the 9.99 availability, because you look at the number of hours that the equipment's been running, how long it was running before those failures were experienced, and that's how you kind of get to this number at a high level. So extremely high levels of reliability, mathematically proven based on products that are actually in the field and in operation with customers today, and real world data, not theoretical or experimental data. We've been talking a lot, and I've been focusing around automatic transfer switches, which you can see here on the left-hand side. But there is another style of transfer switch that also falls into our 7000 series, which is a bypass isolation transfer switch. Bypass isolation transfer switches are almost like two transfer switches in one that go into ultra high reliability applications such as healthcare, data center, supercritical loads, where you want to be able to have a way to bypass the primary ATS to do service, but you can't afford to take your loads offline to do that service. So a standard ATS, to service it, you most likely have to take it offline, which means your loads have to go online. But in applications such as a hospital, you can't afford to do that. So the way to do that is use a bypass transfer switch that allows you to bypass power directly to the load, de-energize the primary ATS completely, and do your service and maintenance on it without the load ever feeling an impact. And an extra bonus is that the extra handle on the bypass switch can also serve as an emergency backup should you want to manually operate the equipment as well. So to talk a little bit more and show a little bit more detail on the manual bypass isolation transfer switches, we do have another video where I'm going to walk you through one of those pieces of equipment.
Hi, my name is Victor Bonaccia. I'm the Director of Product Strategy here at ASCO Power Technologies. And I'm back again today to show you our bypass isolation transfer switches in our 7000 series platform. In a previous video you may have seen, I talked about our standard transfer switch designs in the 7000 series platform. The bypass isolation design is basically a scaled up, more redundant version of that. While a standard transfer switch provides a single device that lets you transfer between sources, this provides you one primary switch on the bottom that is operating 90% of the time, carrying power to your loads from your sources. However, it also provides you with a secondary manual switch on the top that can be used for certain applications. The main reason someone would want or use a bypass transfer switch is for one of three reasons. It allows you to bypass the primary switch and put it into a test position, allowing you to operate the bottom switch, proving its operation and testing requirements without impacting your load, since they will be fed by the top bypassed unit. The second reason is you can rack out the bottom switch all the way out to an isolate position, completely de-energizing it. That allows somebody to open the bottom door, perform service, inspections, and maintenance on the bottom switch, again, without impacting your customer or your loads whatsoever. Lastly, should the bottom switch be out of service for any reason, manual transfers can be accomplished using the top manual switch at any point, providing a degree of redundancy and increased reliability in your overall system. Our 7000 series bypass isolation transfer switches have a lot of the same pieces that a standard switch has. It uses the same main controller, the same indicator lights and controls. However, there are key pieces that are added. The handles are permanently affixed, ensuring that they do not get lost or damaged during the life of the equipment, which provide your bypass and isolating functions. Additionally, a bypass isolation display controller provides indication of the additional bypass statuses that are inherent to this type of equipment. In this example, it's de-energized since the equipment is not on, but it contains LEDs showing the status of the secondary switch and the primary switch, LEDs showing the status of the sources, as well as a toggle switch to manually start the generator should the primary controller be out of service during maintenance. A bypass isolation transfer switch, as I mentioned before, is really composed of two transfer switches. A bottom switch, which serves as your primary switch and is operating most of the time. Allow me to show you that switch now on this de-energized example. The bottom switch is very similar to the transfer switch you saw in our standard ATS video. It has the same solenoid operator and capabilities as the primary switch, the same contacts, and the same overall structure. However, it includes interlocks and additional busing that connects it to the secondary manual switch on the top of the equipment. On the top of the equipment, as you can see, we have a very similar switch to the bottom with identical current, short circuit, and electrical characteristics as the bottom switch, except it is operated by a manual handle to allow bypassing of that bottom unit. The bypass sequence of operation is actually a very simple operation. The way I like to explain it to people is using the acronym BIB, B-I-B. Bypass, isolate, bypass. This unit's de-energized for the purpose of this demonstration. However, let me walk you through the sequence. Imagine the equipment is connected to your utility power source and that the utility power source is good. In the example that someone would like to do a test on the main bottom transfer switch, they would start off by approaching the equipment. They would turn the bypass handle, connecting it to the normal power source. This will be represented both with a mechanical flag indicator on the door as well as an LED light on the top status panel when energized. It includes all the interlocks to ensure that you do not parallel the sources by accidentally connecting it to the emergency source. Once you are bypassed to the utility source, there are actually two paths of power to your loads, one going through the primary switch and one going through the secondary switch. Normally, you would not be able to rack out the primary switch unless it were bypassed to that source. But because we are bypassed, the required safety interlocks have now been released, which will allow me to turn this handle, taking the bottom ATS to the test position. In the test position, the bottom unit is now disconnected from the primary conductors. However, it still has control power, so it can be transferred back and forth. Since the primary power conductors are disconnected, it does not impact your loads as you transfer the unit back and forth. However, if you continue turning the isolate handle, it will then take you out to the isolate state. In the isolate state, it is now completely de-energized on the bottom switch, making it safe to do service. The unit can then use its integrated rails to be racked out, allowing easy access to all the main serviceable components of the equipment. In the unlikely event that the primary bottom switch is out of service for an extended period of time, and an outage occurs or you want to connect to generator power for any reason, a bypass isolation transfer switch gives you that capability. If you close the bottom door, the top bypass mechanism can still be used as a manual switch. Remember that the bottom switch is completely electrically isolated from your system. So the top handle can now be disconnected from the normal source and reconnected to the emergency source, allowing you to connect to a generator or other emergency power source. So once again, the operation is very easy using the BIB acronym. Bypass it to the source you are connected to, isolate it to do your testing and servicing, and then bypass it again if you so choose to another power source.
Hopefully the walkthrough of the bypass switch helped you better understand the applications and how to operate the bypass switch. Of course, these are very high-level overviews, so if there's any questions on it, feel free to reach out to any of us after the webcast. But now we're going to move on to talking a little bit more about the controls of a 7000 series transfer switch. The transfer switch, whether it's an ATS or a bypass style, a standard switch or a bypass style switch, is equipped with a controller. And in our products today is the Group 5 controller, which, as I mentioned, serves as the brain of the equipment, taking care of all the monitoring, all the sensing of the voltages and frequency on the equipment, and then using that information to decide what kind of actions to take and whether or not to initiate a transfer. One of the primary requirements of the controller is to determine the source health and the acceptability. So using the voltage and frequency, which is what most ATS controllers need to sense at a minimum, we can determine if there's an under-over voltage situation, an under-over frequency situation, voltage imbalance, or phase rotation mismatch from what the equipment suspects. The controller has a nominal parameter in it. A user can go in and decide on a range of values what's considered under voltage or over voltage based on their application, meaning some applications, such as healthcare with an MRI machine, may be much more sensitive than, say, other equipment in an industrial plant, which is not as sensitive to small power fluctuations. So you can customize the ranges of those based on your geography and the power quality at your facility, as well as the application that it's protecting. The controller does have a screen in the front that can be used to make those configurations. Now, many of those configurations, such as voltage, like I mentioned, is configured using the concept of a pickup and a dropout. The pickup and dropout works very similar to the way a thermostat works in your home. When you set your dropout value, it does not necessarily mean that when you exceed your dropout value, which is the point at which your source is considered bad or unacceptable power for your loads, it does not immediately consider it good the moment it crosses that same threshold again. And the reason is because if the power is sitting right at that level and bouncing just above and below it, you do not want to constantly be transferring the equipment back and forth, or transfer or starting and stopping the generator. So there is actually a gap between it between declaring the source bad at your dropout and a significant improvement before it is considered good again, which is your pickup. Just like a thermostat at home, where you do not want to start and stop the air conditioning every 5 seconds because you set the temperature at 70 degrees and now it's 70.1 or 69.9. So that provides a greater level of control. And even though this diagram is based on nominal voltage, the same concept can be applied to over voltage, to frequency, and everything overall. A common transfer sequence and transfer sequence has many steps to it. We don't immediately start a transfer. So first thing that happens is when, say, a blackout happens, there is a source failure delay to make sure the source really did fail. If there's a transient or a short circuit that is pulling down the voltage, we want to make sure if it's somewhere else in the system that the breakers have time to clear that fault, or if it is a momentary transient that can resolve itself before you nuisance start the generator. So we wait a short time delay before starting the generator. When the generator is started, we wait for it to come up to proper voltage. And once it comes up to proper voltage, we wait an additional delay, which again can be user configured, the duration, or completely eliminated, but commonly is set to a short duration to allow the generator a little bit additional time to stabilize its voltage, as well as if you have multiple switches in the equipment, you can set different transfer switches to different time delays. So ATS1 transfers at 5 seconds, number 2 at 10 seconds, number 3 at 15 seconds, so that they do not all transfer at once and block load the generator, causing potential issues. Once that time delay expires, we go ahead and transfer. There's a lot of different types of transfers that can happen. And then we just wait for the utility to return. Once the utility returns, we wait another time delay to ensure it really is back and not, again, an unstable source. And then we go, once it's returned for a significant period of time, again, user definable, we go ahead and retransfer the switch to generator power. The last step we take is to run the generator for a short period after disconnecting from it to ensure it has time to cool down properly before shutting it off for good. And you got to make sure to coordinate that with your generator controller to make sure you don't accidentally have two cool down periods running back to back to each other. I'll try to move very quickly because I know we're out of time here, but I just have 3 more slides, I believe it is. As I mentioned, a transfer is something that is very often generalized, but there are many different types of transfers. The first and most common is an open transition transfer, which is break before make type transfer, where both sets of contacts are usually connected to a single shaft. And as the shaft opens from one source and the contacts open from one source, they are simultaneously connecting on another source. On the way to transfer from source 1 to source 2, for example. This, in a hot-to-hot transfer scenario, that does resolve in a very short transient between 40 to 80 milliseconds, depending on the size of your transfer switch. However, this is still considered to be a very, very fast transfer and allows for a feature called in-phase transfer. In-phase transfer is used when you're transferring hot to hot, so during a test situation or when connecting back to utility after being on generator, and wait to initiate the transfer when both sources are synchronized to each other. As you can see here, the sources are out of sync, one source being the gray line and the other one being the pink line, and when they become in sync, they go ahead and that's when the transfer is initiated. That's important because by making sure the two sources are closely synchronized, it minimizes the number of electrical transients to your system, especially when you have large inductive loads such as motors and pumps. So they'll help prevent nuisance tripping of breakers on those pieces of equipment and protect them from physical damage due to those transients if you do transfer out of phase from one source to the other. Another option if you have large motor loads is to use a delayed transition transfer switch, which is still a break before make transfer switch. But the difference, as I mentioned in the videos, is that it provides you two independent shafts that can be independently controlled. And that means that one source can actually open and stay disconnected from both sources for a period of time, and then reconnect on the other source. This again is another great way to protect large motor loads such as wastewater applications, and allow your source to disconnect, wait for any residual energy in a rotating load such as a pump or a motor to dissipate and wind down before connecting it to another source. So this is a great option to use for motor applications and pump applications in large scales. The last mode that I'll cover today is the closed transition mode. Closed transition switching is actually a make before break operation, and actually does the opposite that you usually see a transfer switch do. Usually the job of a transfer switch is to ensure that you are never paralleling two different sources of power. Well, a closed transition transfer switch monitors several parameters within it, and when those parameters all align and the sources are passively synchronized, it goes ahead and actually closes source 2 before opening source 1. So meaning there is a momentary parallel operation. Now, the great thing about this is that it means that during a retransfer or a test, your loads are not exposed to any outage whatsoever, and that these transitions can happen transparent to anyone in the facility or the loads. It's very effective. However, for it to happen, like I mentioned, there are several rules that have to be followed. The frequencies must be matching within less than 0.2 hertz of each other. The voltages must be within 5% of each other. There cannot be a phase angle difference greater than 5 degrees. And all this is done by monitoring the two sources relative to each other passively. We are not controlling or doing synchronization with the equipment, but the thing is that generator frequencies tend to be slightly higher than utility frequencies. For example, operating at 60.1 hertz versus 60 hertz, and they will naturally drift in and out of synchronization with each other due to that. I like to explain this by imagining two race cars going around a track. If two race cars start at opposite ends and go exactly the same speed, they will never cross each other and they will never synchronize. But if one race car is going slightly faster than the other race car, it will eventually catch up to it, which is the same thing as being synchronized momentarily before it passes it again. So that's how the concept of the passive synchronization that happens with closed transition happens, allowing for a safe parallel operation. Additionally, there's all sorts of protection and time delays that ensure that if the parallel operation lasts for an extended period of time, longer than is safe, it will trip outputs on the transfer switch that are meant to be connected to circuit breakers elsewhere in the system to end the parallel operation. So I'm a little bit over time, but I think that concludes my slides and my presentation. I'll give it to Jorge now to see if he has any questions or last second questions we can fit in before we conclude. Jorge? Jorge, you are muted still.
Muchas gracias, Víctor, por esta excelente presentación. Dado que estamos un poco excedidos en tiempo, vamos a hacer un par de preguntas muy rápido. La primera pregunta, what are the main considerations to take into account when selecting an ATS?
So there's a lot of things. Some of the most obvious ones are, what are the electrical ratings that you're concerned with? You need to make sure that the amp size, the current that the ATS is going to handle is properly sized. The voltage is correct. Where are you going to install the equipment? If it's going to be indoors or outdoors, it will determine what kind of enclosure should be provided with it. Based on the application, you also you may select different type of transition modes, such as delayed or closed transition. All things that are really dependent on your application and how you plan on using and installing the equipment. And of course, the WCR value. Like I mentioned when we spoke about standards, you want to make sure that the withstand rating of the transfer switch is coordinated for where it will be installed in the system and relative to what other circuit breakers and equipment is in the system, so that you don't over or under engineer the transfer switch design or the overall electrical system design.
Muchas gracias, Víctor. Y una última pregunta. If we have a large motor load, what type of transfer switch should I purchase?
Yeah, so actually, that was one of my last slides. So there's really two solutions for large motor loads. The preferred solution is a delayed transition transfer switch. As I mentioned, a delayed transition transfer switch can be used to disconnect from one source, wait a period of time for the large motor or pump to stop spinning and lose all its momentum and residual energy before connecting it to another source, making it a very safe, effective transfer and very predictable. That avoids any transients that may happen from the motor connecting to a source that it's no longer synchronized to. Another alternative option is, and usually recommended for smaller motors only, is a in-phase monitor with the open transition, where we can monitor the two sources and wait until they are synchronized to each other in terms of phase angle before transferring, which again would mean that we minimize the amount of transients and electrical currents and eddy currents that could occur within the pumps or the motors that could damage them. So delayed transition is the number one recommendation, or if it's a smaller motor or cost is a major concern, open transition with an in-phase monitor would be the second recommendation.
Muy bien, muchas gracias, Víctor. Hemos agotado el tiempo de nuestro evento para el día de hoy. Quisiéramos en nombre de Schneider Electric y ASCO Power Technologies agradecerles por su participación. Agradecemos también a nuestro speaker. Esperamos que el evento haya resultado de su agrado y la información compartida les sea de utilidad para presentes y futuros proyectos. Una vez más, la grabación del evento quedará disponible con subtítulos para que pueda ser consultada posteriormente. Les dejaremos saber en cuanto esté listo. Mi nombre es Jorge Parapar nuevamente. Gracias por su tiempo y muy buenas tardes.
Gracias a todo el mundo.